Hello, welcome to Clojure North 2020. I'm going to talk about building reliable, scalable services with Clojure and Core.async. I am Kapil Reddy. Little change of plans. I'll be only focusing on building reliable services with Clojure and Core.async because getting the reliable part right is quite cumbersome, and we'll see is why is that the case. A little bit about myself. I'm a Clojure engineer at HelpShift. I work on distributed systems. In my free time, I like to read graphic novels. I study film and theater when I get the time. A little bit about HelpShift. HelpShift is a enterprise grade CRM product. Uh, we try to connect our brands to customers through conventional channels like email and voice, as well as with the modern mobile messaging as well. Some of the brands that we have on board are Microsoft, Supercell, and Singer. The scale that we are at right now is 1.2 billion device installs. This number is a few months old, so expect this number to be slightly higher. Some of our front-end services serve requests around 150K. We try to keep our response times very low, as low as 50 milliseconds. Uh, our hourly traffic is somewhere around 400 GBs, and we have at peak around more than 1000 VMs deployed. Uh, the outline of this talk is going to be, I'm going to talk about a problem which is going to be a bulk write service. I'm going to talk about the solution using Core.async. Then we are going to talk about improvements and comparisons with other approaches, and then we are going to conclude and see what we have learned throughout this journey. So first, the problem, right? So this is a very simple outline. We have a bulk write service. That's what we are going to look at. It's consuming from Kafka, and it's doing bulk updates to Elasticsearch. So this is what we are interested in. But since we are trying to build a reliable service, we are also interested in these two dependencies, especially this part where we are going to handle all the failures and all the complex scenarios that these two dependencies can throw at us. Especially handling Elasticsearch failures and its scenarios becomes much difficult because we are writing to it. So let's take a look at the components of this bulk write service. Of course, there's like a core namespace and a core component, which is the glue logic and which is holding all other components together. One of it is Kafka consumer, second is HTTP client, which is going to talk to Elasticsearch, and third is just monitoring and health check component, which is going to keep track of health of all the components. Going down to the code, this is the simplest version of this code, which is just a function to Kafka library calling consume. It's asking to consume from ES updates topic. It creates a lazy sequence, and we are running a doseek on it, which will run indefinitely. The moment we have a new message on this topic, we are going to call a HTTP post, which is pointing to Elasticsearch. But this is not bulk update, so we'll change this code slightly, and now we have changed it to accomodate accumulate around 100 messages, and if it hits 100 messages, we'll do a bulk post to Elasticsearch. Here we are assuming that all the bulk API is being followed for Elasticsearch and it's working as it's supposed to. But there's a problem here. There's a better alternative to doing this, which is Elasticsearch itself. Elasticsearch has a Java library which provides a bulk API. This is much more efficient because it's working on TCP, and they have it's tested thoroughly, so it makes sense to use that. The API for this is you initialize the bulk updater object. It has two callbacks. One of it is success and other is error. We are using this in doseek where we are saying bulk process update, and that's about it. In success, you'll get both the events of when the bulk process started and when it stopped successfully, when the bulk process was done completely. There can be errors, and this callback will show those errors. But there's a problem in this approach also. In this older approach, when we were just calling a HTTP endpoint through a HTTP client, this was a synchronous operation, and if there was something wrong, we could just catch this error and handle it. In this case, this bulk process update is asynchronous. So problem is anything that can go wrong will just show up on the error or on the success callback, depending on the type of failure or the type of complexity that shows up. So since this is asynchronous, there is one more problem that is happening here, which is if you keep consuming from Kafka and there are a lot of messages, even though there is a bulk process that triggers based on the size of message, based on the count of the messages, or there can be a time-based trigger also, because we are using the Elasticsearch Java object. When it triggers, there is nothing stopping from this doseek to consume more messages, and this leads to a bigger problem. We can look at this problem from a different point of view of timeline. We have a Kafka consumer, it is initialized, and we have a ES bulk processor which is also initialized. Kafka consumer is consuming. At T12, ES bulk processor decides based on the number of messages it has accumulated that let's do a bulk update, and it completes that bulk update at T22. From T12 to T22, Kafka consumer is still consuming messages because the doseek has no notion of stopping. So there are two problems here. There is possible data loss because the way Kafka offset management works, and if you are using auto offset management, you are consuming messages and also committing the offset, which means if we restart somewhere around T22, we have committed the offsets and there is just data loss because nobody has even Elasticsearch has not seen these updates. Also, since you are consuming this indefinitely, there can be a memory footprint issue. Now we have machines that have a lot of memory these days, so we are going to put that issue aside and just think about just the data loss. And still it's a big problem because we can potentially lose customer data. So what do we do here? So we have this asynchronous function call. So let's list down the problems first. So we have uncontrolled consumption, which means there's no way to tell this doseek to stop consuming when something is happening. There is partial and complete failure from ES, which we don't know how to handle because it's in a callback. And there is also a case of degraded ES where Elasticsearch itself can go into different states. If you have worked with Elasticsearch, you know there are like green, orange, and red states. It can go into that, and we probably don't want to handle all of those cases. At this point, we all have been here where we start looking like this, and we are just hating all these complexities. Eventually, since we are Clojure engineers and we are deep thinkers, we'll eventually start wondering about the problem and how to solve this. So we'll ask, what can we do better here? So let's look at this code and try to fix it. So we said, okay, fine, we'll try to add error handling by using try and catch, and we'll also throw errors from the callbacks. Now we are assuming here that the Java object will bubble up the errors, and our try plus catch will actually handle even the ES exceptions. This is for the moment we can assume that this actually happens, and let's go ahead with that, but there are still bigger problems. So in case of degraded ES, our infra team or ops teams can come to us and say, hey, when ES goes into red and there's some problem going on with that data store, don't update or don't run your bulk process. Can you do that? And again, here there is no way for us to tell that ES has gone into a red state, and no way to stop the doseek. Again, we start looking like this, but again, eventually we'll start figuring out, okay, can we do this in a better way? So here we eventually end up on something related. We'll try different solutions and we'll figure out, okay, can I use Core.async here? This seems like a problem of different threads doing different things, can I connect them together and like coordinate between everything? At this moment, if you don't know what core async is, or you don't know its primitives, I suggest that you pause this video and go to this link. This is a nice primer on what all primitives are there and how they are used. Okay, so now just to boil down the problem, what we are facing is there are like these three blocks of code which don't have any relation with each other, and that's what we want, right? We want some coordination between these three parts. With core async, the simplest thing you can do is take a channel and put everything in that channel. So that's what exactly we are doing here. We are taking all the events that are generated by success callback, which is bulk start, bulk stop, all the events by error callback, and also we are putting all the data that is consumed by Kafka consumer into the same channel. Now what do we do with this channel? We create a go loop. So this is how this go loop looks like. We have a case where we are handling events based on their types. If there is a message, we are saying okay, send it for bulk process update, and repeat the whole thing. Now this is not doing anything differently. This is the same as our previous code, which leads to the same problem of consuming while there is a bulk update going on. How can we solve this? So again, looking at this, can we do something better here? So here we'll pause and think about these two blocks. So this block is basically generating events which are signals to our program to change state. They are not exactly the data that we want to process or store, but they are control events. So we are going to create a control channel and put everything in these callbacks into a control channel. But this part is actually data which we want to store. So what we are going to do here now is store this, create a data channel and push all the Kafka message into that. Now how does our go loop look like now? First of all, we have an initial state which is just init. We have not generated it from anywhere, but it's a good starting point. Now we have this case where one of the cases can be init, and let's assume it's init, and let's not look at bulk stop at partial error for this moment. If it is init, we have a alt between data channel, control channel, and it's just saying that whichever gets a message, just go into that code path. So it's like a con for core async channels, and we are saying okay, mostly we are going to consume from Kafka and VR, and it is going to send it for bulk process update. It's going to recur. The state is still in it, and it's going to end up here, and it's going to consume more and more Kafka messages. Eventually this bulk process object is going to trigger bulk start, which will end up on this code path, because now this alt has now gone into this control channel path, and now it says okay, something has changed and I'm going to recur again, and it is going to stop here, which is bulk start. Now if you notice, in this code path there is no consumption from Kafka consumer or data channel. So it's just going to wait indefinitely for the next message on control channel, which is going to be bulk stop. Once that triggers, we go back to our old consumption and it continues. But if you look at our timing diagrams, what this changes is now it is behaving slightly differently. We have a Kafka consumer, it is consuming, meanwhile the bulk processor are idle. At T12, bulk processor has triggered bulk update, and our Kafka consumer is now idle, because in this case there is nothing that we are consuming from data channel, right? And since a put will be indefinitely blocked on a data channel if nobody is consuming from it, the do-seek will also indefinitely wait for that Kafka consumption. So we are not consuming more messages now. So we have solved consuming more messages. So we have solved both the memory footprint problem and Kafka messy Kafka offset management in this case. Okay, so we have solved uncontrolled consumption. what about partial and complete failures from ES? So before even going for partial failures, let's take a look at degraded ES. And this is not the same go loop. We have created a new loop, and what we are saying is I want to know the state of Elasticsearch cluster, and just a loop which is like just polling Elasticsearch cluster every 5 seconds. Once it gets any status, it's just putting it into the same control channel with new types, which is ES green, red, down, and unknown. Now how do we use this in our go loop? We have more conditions. So when we see red, we say okay, don't do anything, just wait for the next control channel, which will be ES green, and then you can go back to consuming from Kafka and triggering bulk update. If we know that Elasticsearch is down, we can just say there's no point in running this service, might as well shut down this service and let operations teams handle it once they get Elasticsearch back up. The same way, if we see slow responses from ES update callback, we'll say okay, slow down a bit, and this can be again like an exponential back off if we see slow responses again and again, and eventually we can even stop the service depending on how many times we have seen the slow updates. Alright, so we have covered the degraded ES, and we have also covered partial failures through slow updates and errors. Actually, we have just covered ES slow and red, but we'll come to the partial failures when we are talking about retries. So when we see partial errors, we can call the retry bulk process, which is again a method that is provided by the Java object, and we can just call that and wait for the control channel. Again, we are not consuming for Kafka, so there is no possibility of data loss. This can be even more sophisticated, where we can keep track of retries also in this recur, and we can say that after X number of retries there's nothing better we can do, and we'll shut down the service. So we have taken care of partial failures, we have taken care of retries, we have taken care of degraded ES and uncontrolled consumption. So we have come from this point now to this point. Okay, so we are going to also look at a small demo which will highlight this case again. So I have this implementation where we started, which with the ES bulk updater. There are 2 callbacks and they're not doing much. There is no handling here, and I am stubbing events which are Kafka message 1, 2, then bulk process starts, and there is the third message which should not be consumed, and success should happen first, and then 3 and 4 should be consumed consecutively. So when I run this is going to show what was in what orders event happened and how the system behaved. So if you see here, the system behavior is not desirable. During ES bulk start, between bulk start and bulk success, there was a consumption that happened from Kafka message 3. Now there is a second implementation which is slightly similar but not exact to our go loop approach. Let's try to run that. Now the system behavior, in this case the events are exactly the same for the first test and the second test. Here bulk start happened, bulk success happened, and then we consume third and fourth message. This code is going to be up on GitHub. I am going to post the link during the talk or in the description of the video. Let's get back here. Alright, so looking at this loop, this is great. This is like a really clean code, and this solves all our problems, but there is a common pattern that is happening here. And again, like as Clojure engineers, we get inquisitive and we want to know if we can borrow any we can like find some common patterns, or are there concepts that we can borrow from other languages where this pattern has already emerged. And this leads to us to thinking more about where have we seen this. And Erlang has this pattern, and they already have primitives to handle such cases. Since Erlang is a message passing language and it's much older, they have already developed a lot of primitives and tooling around it. This is called Gen FSM, and now it is the newer version of this is called Gen State M. Basically what it does, I won't go into the code of Erlang because I don't know how to write Erlang, but I like highlight some of the codes from books and documentation. So this is a code from Learn You Some Erlang. This is from a chapter on finite state machine. So basically Gen FSM behavior is similar to Gen server behavior in Erlang, just that Gen FSM is supposed to be handling synchronous and asynchronous events. This is somewhat similar to what our Go loop was doing. Okay, another definition in Erlang's documentation is a finite state machine is something that can be described as a state applied to an event will generate actions and a new state. Okay, this sounds interesting. This is also something that we are doing. Okay, so can we make this even better? Can we like make it so that it follows something that can be repeatable and can be used in some other cases also? Okay, so we have restructured this code and we have created this new loop called Go as FSM. This takes a control channel, and what this says is, okay, I have a state that you can match of this Go FSM, and it maintains its own state, and if it receives this event, switch to this new state called bulk in progress. So if you are consuming and bulk starts, then switch to this process state. Same way, if this is the previous state, if either of these are the previous state, consuming, bulk stop are init, and if I see a new message on data chan and internally it will use an alt, do these actions and create this state which is consuming, and so on. We have like basically recoded it to follow this new convention. So this is a library that is at works, and this is still in work in progress, but this is how the DSL looks like, where we can generate FSM using Core.async and its Core.async and Core.async channels. Since we are defining it in a very particular format, you can also generate a diagram of state transitions and events that cause the state transitions. This is also a really great examples of how macros can work here and translate this to workable code also, and also generate documentation by itself. Okay, some of the observations from this exercise. One of it is CSP is definitely not message passing. So Erlang and Core.async are two different paradigms. We should not mix them, but there are some ideas that we can borrow from Erlang. One of the problems that we have seen in this approach is balance of which channels should be blocking and which channels should be non-blocking can be very tricky. General guideline is a data channel should be blocking because you don't want data loss, and control channels should be non-blocking just because of the fact that there can be multiple producers and all of them can produce to the same channel, so there can be a lot of deadlocks. So usually they become non-blocking, and this is something that even Erlang follows for GenFSM. Tooling is of course required for writing complicated Go FSMs. There is not enough tooling that is built for debugging a Go FSM, and we are constantly thinking about better ways to do this. Testing Go FSM is actually straightforward because in itself it is not depending on anything external. All it is depending on is channel and a bunch of events and data in a particular order, and you can create different scenarios that you wouldn't be able to create in production or like in real with real databases. Applications of Go FSM backend services that are talking to multiple dependencies and want to handle complex scenarios, this is a great application. UI components consuming from multiple event streams can be another great application. And I would like to know, like, if there are more applications that you can think about. GoFSM at HelpShift is kind of tested with a service called Kaioken. Yes, it is a homage to Dragon Ball Z. It's a move which happens for really short time, but it takes a lot of toll on Goku. We are using it as sync for Elasticsearch and MongoDB. It has been in production for 2 years. We have seen some hiccups with limbo states where like the FSM goes in some weird state, but it can be easily debugged because you can keep like track of last few events and just log them if it goes into this particular limbo state. It is doing a humble RPS of 300 on a single instance. Conclusions of this talk: FSM plus core async can be used to handle complex cases. Core async channels can be good for interfacing between different systems or different components. And there is, of course, there is a lot to learn from other languages and their offerings. Thank you.